Welcome to CSE 455B Deep Learning. This is the Piazza link for the course. The course materials will be available on Piazza. The book that we'll be following for the course is Deep Learning by Ian Goodfellow. The e-version of the book is available at deeplearningbook.org. The presentations are adapted from the Deep Learning course offered by Professor Mitesh Kapra of IIT Madras. Our course is divided into 5 units. The unit 1 talks about the MP neurons, thresholding logic, the perceptrons, and the multi-level perceptrons. Unit 2 talks about the feed-forward neural networks and various optimization algorithms. Unit 3 talks about the principal component analysis, regularization and autoencoders. Unit 4 talks about the convolutional neural networks, and Unit 5 talks about the recurrent neural networks. The introduction of the course. Artificial intelligence is a superset under which we have machine learning, and under that we have deep learning. The artificial intelligence is a science under which we want to embed the natural level intelligence into the machines. That is, we want to give machines the reasoning capabilities that humans have. Now coming to the machine learning, the classic definition of machine learning as quoted by Tom M. Michel, it says a computer program is said to learn from experience E with respect to some class of task T and a performance measure P if its performance at the task in T as measured by P improves with experience E. Let's make an analogy of this definition by saying there is a student who has enrolled into the course. That means on the first day, the student is having zero experience of that course. So that means E is zero on the first day. The T, that is the task is to learn the concepts of that course. And the performance measure P, P is the grading that will be done when the student writes the exam. Now, the student is asked on the first day itself to write an examination. Now what happens, the experience is zero here. The task is understanding the concepts, and we are asking the students to write the examination. It's expected that the student will perform poorly. Now what happens after that examination? The student attends the semester, the entire semester. That is, the student attends all the lectures, goes through all the course materials, and at the end of the semester, again the student is asked to write the rest. Now the experience has increased from zero to some finite value. The task remains the same. Now it's expected that the performance is bound to increase. So that means the student is bound to get a better grade. Now, if that happens, we say that the student has learned. So that is what the machine learning is. Now coming to the deep learning. As we know, deep learning is a discussion about the artificial neural networks, the neural networks. So that means in neural networks, what we have is the different layers. That is what deep learning says is a method of representational learning method which with multiple levels of representation. It transforms the representation at one level to the representation at a higher, slightly more abstract level. So it means that when we are giving input to the neural network, the representation of input at the first layer is different, and as we go along into the neural network, the representation changes. That means now we are having more abstract levels of representation. The third point is a very important point here. It says the key aspect of the deep learning is that these layers are not designed by human engineers. They are learned from the data using a general purpose learning procedure. So it means that the deep learning models, the parameters of the deep learning are not tuned by the human expert. Instead, they are being automatically done, and they are being done based on data. This approach is completely a contrasting approach to the traditional traditional machine learning approach that we have. In that case, there is a human expert which tells us about the features that we need to extract from a certain input in order to get the classification or other forms of machine learning models. But in deep learning, there is no human expert required. You just need to have a model and the data. The model learns from the data itself. Coming to the introduction of the deep learning, since here we are talking about the artificial neural network, the artificial neural networks are inspired by the human brain and the interaction between the neurons. Here, the ANNs are not meant to be the realistic models of the brain. Instead, they are just the approximatory models of the brain. They are just the approximations. And talking about the models of the neurons, the Michelson-Pitts neuron back in 1943, it was one of the first models that was being built for of the neuron. It was basically a binary classification model. In that case, parameters were not being learned automatically. You needed to do that manually. Then in 1950, the perceptron algorithm came along, that was published by Van Rosenblatt. Here we automatically learned. Here we automatically Here we automatically learned the weights, that is the parameters. Now coming to the inspiration of today's artificial neural networks, that is the biological neurons. For biological neurons, the research started with the reticular theory back in 1871. So the scientist named Joseph von Garlech, he proposed that the nervous system in the human body is a continuous network, as opposed to what we know today. Back in 1871, he said that our nervous system is basically a single entity rather than discrete cells. Then came the staining technique that was given by Camillo Golgi. He discovered a chemical reaction that allowed him to examine nervous tissues in much greater detail. So now he was also the supporter of the reticular theory. He also said that our nervous system is composed of a single cell rather than many discrete cells. Then in 1888 came the neuron doctrine by Ramon Y. Cajal. He said he used the staining technique and said that our nervous system is basically made up of large number of cells as opposed to what reticular theory said. So basically now we have the neuron doctrine as we know of today. So it came back in 1888. And then the term neuron was given back in 1891 by Wilhelm Gottfried. So he also said that the neuron doctrine is the correct way of looking at the nervous system. So back in 1906, it was very confusing. The world hadn't come to terms with the whether a nervous system is composed of a single entity or is composed of different number of cells. So what happened back in 1906? The Nobel Prize was shared between these two persons, these two scientists. So that means both the reticular theory as well as the neuron doctrine was awarded the Nobel Prize. And then in 1950, then in 1950s, the electron microscope came along, and finally we have the confirmation of the neuron doctrine. That means the nervous system is not a single entity; is composed of large number of neurons. That is the interconnection of nervous cells. So that was how the concept of neurons came along. Now we'll see what happens to the artificial intelligence. So that means modeling of these neurons. The first such model came as Michael-Spitz neuron. So that means back in 1943, we have the first such model. It is a highly simplified model. So in that case, what we have is we have set of inputs. That means x1, x2 to xn. So these inputs were binary, and it goes through a certain function g, and then we get an output that is a binary output. So it was basically a binary classifier. So this concept was given back in 1943. So we even call this as MP neuron. Then came the concept of perceptron. The perceptron model came along in 1957. The term perceptron eventually will be able to make learning decisions. So here you see there is a clear difference here. So that means here for x1, x2, xn, these arrows do not have any entity written out there. So that means there are no parameters which are being learned here. Everything is being tuned by humans. But here, basically we have the parameters associated with every input, and that is where we say the actual learning came into play. The first time the actual learning came into play, that was with perceptrons. Now this is an image of an embryo of an electronic microscope, which back in 1958 it said that it's an electronic microscope which expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. So this is in New York Times back in 1958. That is what the perceptron was. Then we have Iwakimo. He is the first person who gave the first generation of multi-layer perceptrons. So here you can say you have multi-layer representation perceptron. So we have an input layer where we give our inputs x1, x2 all the way to xn. Then we have the first hidden layer, second hidden layer, third hidden layer, and so on. So the concept of multi-layer perceptrons came in 1965. Then we have the perceptron limitations. In 1968, 1969, there was a famous book called as Perceptron, and the authors of the book, Minsky and Papert, they outlined what a perceptron could and could not do. And this is a simple example of what a perceptron cannot do. On the top right hand side of the screen, you have an XOR, a simple XOR. And Minsky and Papert, they discussed in this book that the perceptrons are very limited. They will not be able to even solve the simple problem as perceptron, because as we know, in perceptron there cannot be a linear boundary. We can never draw a linear boundary in this perceptron where we can divide positive and the negative cases. This was a major setback. This was a major setback for the research in AI, and it almost stopped entire thing what happened in AI. All the funding, all the research stopped after the publication of this book. Then came the concept of backpropagation. The concept of backpropagation was discovered and rediscovered several times throughout 1960s and 70s. Then again in verbose, and then again in 1982, it was first used in the context of artificial neural networks. The concept was already there. That is, a mathematical concept of backpropagation was already there. But in 1982, it was first used in the context of artificial neural networks. Eventually, it was being popularized by Rumerhult in 1986. So that means that is why the first point here it says it was discovered and rediscovered many number of times. And then finally in 1986, it was Rumerhult which popularized the concept of backpropagation. Then came the concept of gradient descent. The Cauchy discovered the gradient descent motivated by the need to compute the orbit of heavenly bodies. So basically, gradient descent is not something that was discovered with respect to neural networks. It was discovered with respect to orbits. As we know today, even we are using the gradient descent. And then we have the universal approximation theorem. The universal approximation theorem says that if we have a multi-layered network of neurons with a single hidden layer, can be used to approximate any continuous function of any desired precision. So here it basically says when we have a multi-layered network of neurons and with a single hidden layer, we can have any function, any mathematical function can be approximated using that. We saw back in 1986, we had the concept of backpropagation as well as gradient descent, the algorithm that we pretty much use today as well in the large scale neural networks for training. But why couldn't these concepts pick up in 1986 and even in 90s? Because back then we had a lack of large label data sets were not available for us. The computers were too slow to train the neural networks, and the activation functions that we see as of today and that we'll be studying during this course, they were not there. They were not discovered as of at that time. And talking about computers, back in 1960s, it said that NASA, the computational power that is available with NASA, that was available with NASA at that time, is equal to the computational power that we have in our smartphones as of today. So that means these were these were the reasons why in 1980s and in 1990s the concept of deep learning and artificial neural networks could not pick up. And opposed to that, what we have now is that we have faster computers. We have highly optimized hardware, that means the GPUs. We have large label data sets in order of millions of images. If you check ImageNet, a very large data set. We have better understanding of weight initialization functions of what and what does not work. We'll see that in that course. In the course, how do we initialize the weights, and what are the better ways of initialization? And obviously, we have a superior activation functions as opposed to what we had those days. Now, this is the curve that has been taken from a lecture by Andrew Ng. Here it says what a deep learning and machine learning is. You can see that the amount of data, as we increase the amount of data, the machine learning curve tries to bend. So that means after a certain amount, after a certain time, the machine learning stops getting better as we increase the data. But look at the deep learning curve, the blue curve. it starts going up. So that means more the amount of data we have, the better our models are in deep learning, as opposed to what happens in traditional machine learning. So that means we need to extract features by hand. This is how it is. The traditional machine learning is on the left hand side. Here we have the inputs. In that case, let's treat them as images, the input images. Then we handcraft, or we call them as engineering the features. We engineer the features or handcraft the features. Then we give that to the machine learning model or the classifier, and then we get the output. As opposed to that, our deep learning model, we have the input, the simple features. That means we have the layered representation, as was being discussed in the few slides back. We have the layered representation here. The first layer gives us some simpler features like edges. Then we have the intermediate features like the corners. Then we have the more abstract feature like object parts and etc. And after that, finally, we have the output. Now, when we are talking about the deep learning, so the point here is how deep is deep. So in case we are using the specialized neural network architectures such as convolutional neural networks, recurrent neural networks, or LSTMs. So here, yes, we're performing the deep learning. And generally when we say our model has a depth greater than 2, so that means the number of layers, the number of hidden layers that we're having apart from the input and the output layer. If the number of hidden layers that we're having is greater than 2, we say that yes, we are doing the deep learning. And when the number of layers increase by 10, then we can say that we are doing the very deep learning, but it should be just called as deep learning. Thank you.